Who's happy to be done with the paper? Yeah, as fun as I try to make it for you and give you plenty of time, I'm sure you're glad it's behind you, right? So now I get to read them all and have them graded before the end of class semester. I will get them back to you, but yeah, it takes me a while. Which is why I don't let you just have any old word length. If you all wrote like 10-page papers, I'd never finish. So. You guys got any questions about stuff? I know when you leave class, I know you're just thinking about this. It keeps you awake as you're falling asleep. You're going, oh, that I saw. If we did this. You're all thinking more critically, right? And asking more questions. Before I ask Barbara hers, I do at least hope that there's some minimal things I like to dream about that you'll be better off with because of this class. And that's when you hear things in the media, especially from like politicians, you won't just take them blindly. You'll ask questions. You'll like, wait a minute, let me think about that. That's not right. Or let me see. You'll look a little further and say, whoa, wait a second. Okay, that's accurate, but it's kind of skewed a little because we can do a simple test and prove this. But anyway, you go first, Barbara.
You're going to talk about this, but when you say light, and you talk in physics terms, where exactly do you define light in the spectrum?
Where do we define light in the spectrum? Yeah, we will.
Visible light and light you can't see.
Yes, in scientific terms, light is all forms of electromagnetic radiation. So the electromagnetic spectrum are all forms of light.
So if we
Visible light is what we usually are only referring to in normal speech. And yeah, I'm going to show the whole spectrum again today.
So if you call radio waves light,
Would you call radio waves light?
no.
Yeah, a lot of people don't. Are radio waves light now, according to science? Yes. And since you brought it up, how are radio waves and sound waves alike? They're waves. How are they different? Longitudinal and transverse. Yeah, a sound wave is longitudinal. Radio waves is transverse. What else? Their speed. Sound waves travel at the speed of sound. Radio waves travel at the speed of light. What else? Matter, yeah. Sound wave is a mechanical wave and needs a medium to transmit through, like the air or steel. Radio waves don't need anything. What else? If you could see the waves, would they look different? Yeah, the wavelength. Which one's longer? Sound waves and radio waves. It does depend on the frequency, yeah. Good. So I'm glad you asked that one. Okay.
When you were talking about resonance, you said certain objects have their own frequency. I didn't quite understand that. Even if they're not vibrating, they have it. What is that?
Almost any elastic substance I can think of has a natural frequency it wants to vibrate at. Doesn't mean it's necessarily right now vibrating at it. But if it's driven at that frequency, something tries to drive it at that frequency, and it naturally wants to vibrate at that frequency, it'll resonate. And the amplitude will grow. Yeah.
And that's just determined by the material?
Determined by the material, yeah. So even this table. Well, an example, bridges. You've probably heard of bridges that have collapsed. The famous is Tacoma Narrows Bridge in Washington. The wind was blowing, and it wasn't that hard of a wind, but it was at the right frequency. It was shedding off the, Bernoulli effect here. The wind comes by, and it was deflected. So that created differences in pressure on the area. Pressure over area is a force. So there was a driving force causing the pushing on the bridge. And it occurred at the frequency that the bridge naturally wanted to resonate at. So the amplitudes grew, resonance, until it couldn't handle it, and it collapsed. You had one? Sound travels faster in water than in steel? No.
They're both faster than air.
They're both faster in air.
Right, yeah.
Steel's faster than water,
Right.
but yes.
But that doesn't change the amplitude. It's just, it comes to you faster, but it doesn't come to
Yeah, the speed doesn't affect amplitude, or amplitude doesn't affect speed.
Right. Okay.
Just think of a swing. A swing goes back and forth. Or your leg. You know your leg's a pendulum, right, when you're walking? It naturally just kind of wants to swing. Sure, you can try to make it go faster, but naturally. Well, I can do a big amplitude or a small amplitude. But anyway, just rough example. Yeah?
Do people have natural frequencies that can you kill someone with?
Do we have a natural frequency?
With resonance?
We're made up of material, so yes, skin is elastic. You hope. See, it springs back. So there's a natural frequency that we could try to drive that, like a wine glass. If you hit it with the right frequency, not necessarily amplitude, but the right frequency, you can drive it. It'll start vibrating and shatter. They would love to do that for cancer cells. Wouldn't it be great if they have a natural frequency? We could hit them with a certain radiation that vibrates at that same frequency, and only cancer cells or tumor cells resonate at that frequency. They could increase in amplitude and shatter, keeping healthy tissue and cells alive if they have different enough resonant frequencies. That'd be awesome. So, that could be a superhero power, couldn't it? Tommy, you had a question?
No.
Oh, okay.
So why don't people do that? Is it because
Why don't we do that?
there's a risk of damaging
Peop-
regular cells, like the healthy cells?
Yeah. Haven't made it work out yet. Or figured out their natural frequency, or they're different enough. But they don't want to damage enough healthy cells. Radiation right now, chemotherapy and things, unfortunately will damage some healthy cells in addition to and that's why people are always sick. I mean, one reason. It'd be great if we could just isolate the bad guys. Figure that out. The society would be greater, and you'll make money and probably get the Nobel Peace Prize, too. Was it? Good. All right. Resonance. This is good. I hope when we're no longer together, you'll see things in the world around you and better appreciate them. And you'll think of me, good or bad. I mean, I get some people where they look at a rainbow. It's beautiful. And if I start to talk about it, they're like, oh, you're dampening the experience. For some, okay. But for me, it just opens up my eyes to even more of the beauty behind it. Oh, who's a Simpsons fan? I know not everybody is, but there's that one where the teachers go on strike, so the parents are substituting, and the scientist is substituting in one. I think it's Ralphie in the class asks a question. He's up there with one of those poppers, the kid poppers that are really fun until you're a parent. Back and forth, and it just makes the pop noise after noise after noise. You know what I'm talking about? You roll it back. It's like got a handle, kind of like a short vacuum cleaner, and as you roll it back and forth, it pops the balls, and they jiggle. Anyways, he's up there. And Ralphie's, can I try it? He said, no, not until you can appreciate it on as many levels as I do. That's going a little too far, but All right. Quicker questions. Oh, it kicked me off again. All right, we'll open polling. Sound normally travels farther in air when the sound is what? Which things go further? Should be the same channel as always, but let me stop that. Yeah, you can see what some people are thinking. We'll just start it over and see if it works like we're used to. Oh, it's because I'm an idiot. Helps if you plug the receiver in that transmits the channel, right? Go web. Well, you've had plenty of time to think now, right? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Meh. Well, good. I was hoping you didn't miss that one. The idea here is interactions again. The higher frequencies are vibrating faster, so there's going to be more interactions. And every interaction, you're going to convert some of that sound energy into thermal energy. So it won't go as far. It dissipates. So low frequencies that don't interact as much usually go further. Okay? A factory floor vibrates, and as a result, you vibrate when standing on the floor. What is this? I realize we get into several terms. You know, we got constructive interference, destructive interference, superposition, refraction, diffraction, resonance, forced vibration, natural vibration, you know, all these things. So good to review the definitions. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, you guys aren't sure. Well, I'll let you vote again then. Talk with your neighbor. If the factory floor is vibrating already, it's causing you to vibrate. Is that just driving you, or is it making you resonate? Let's see if you guys shift one way or the other here.
It just says it's vibrating, it's not resonating. That's why.
It's polite talking today. Yeah.
For resonance, you'd have to explicitly state that the frequency is matching, right? Or
You're saying for resonance, you'd have to explicitly state that it's
the frequencies are coinciding.
that the frequencies are coinciding. So what? You're choosing A then? Okay, he's voting for A. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Oh, we didn't shift much. All right, we'll just get to it. It's A. So the difference, to clarify, things can vibrate at lots of frequencies. You know, I can look. I'm vibrating, but it doesn't necessarily have to be my natural resonating frequency. Remember my ruler? I didn't bring it out, but I can make this vibrate at a certain frequency. I'm driving it. It's a forced vibration. But naturally it wants to vibrate like this. If the forced vibration, the driving frequency, matches the natural frequency, then it's resonating. Does that make sense? So resonances are when they're in sync, when they match up. The natural and the driving are the same. And the amplitude will increase. So if it's slow like this, boom, 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 boom. If I drive it at the same frequency, it gets bigger. But if I drive it at a faster frequency, it's still vibrating, but I'm forcing it to vibrate at that frequency. It's not at resonance. This is important because we're going to get to that with light. Whether light gets reflected, absorbed, transmitted in different colors, the next 2 lectures, or whether it gets onto resonance or not. All right, what's the next one? So when you tap various objects, they produce characteristic sounds that are related to what? You know, it's like banging on a wine glass. Bung! Or a doorbell. That kind of rings. I tapped it. Ten, 9, 8, 7, 6, 5, 4, 3, 2, 1. Somebody's not playing. There you go. Correct. Good. The natural frequency. You let it vibrate where it wants to, it'll do it naturally. And I forget where I'm at. I want to do this one. The phenomenon of beats is the result of what? Beats, a beat pattern. That wah, 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 wah. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. It's either interference or resonance, you think. Okay, let's talk about beats. I did it with these tuning forks. And if they're the same frequency, you didn't hear the wah wah. But if one was slightly different frequency, you heard a wah 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 wah. And if I made the difference in frequencies even larger, what happened to the beat pattern? It got faster. The difference between the two frequencies, say this was at 100 hertz and this was at 105 hertz. The beat would be 5 hertz. If this was 110 hertz, the beat would be 10 hertz, and it would be faster. So instead of hearing wah, 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 you'd hear wah, 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 wah. But what's causing that? Are we making something resonate? Or are the waves interfering to sound louder and softer? Well, I heard the confident people say interference. But let's see, 37% of you weren't sure. It is interference. If there's slightly different frequencies, at some point the waves are in phase and you hear it loudly. But a little later they get off and out of phase, and so it's quieter. Then in phase, out of phase, in phase, out of phase. That's interference. That's a beat pattern. That's why you hear that slower wah, wah, wah. Okay, I had one more. Didn't mean that button. There we go. When sound undergoes refraction, it undergoes a change in what? And I won't lie, I didn't talk about this one very specifically, but the book did, and this is my last clicker question, so I'll explain it for sure after this. Let's see who already understands this. Refraction, that was when the light bends, it changes mediums. Remember my axle, the two wheels on an axle? The wavefront, one enters a different medium while the other part of the wavefront's still in the initial medium. And it bends, changes direction. It undergoes a change in something. Your hint is that's what makes it bend. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Most of you think C, but there's still some confusion. I'll go ahead and give you the answer. It is C. It's the speed. You can put your clickers away. Let me explain that one a little more. So let's say you have a piece of glass, and outside's air. So glass, air. And we talked about, a wave comes in, an incident wave, and some of the wave will reflect, and the angle in will be the angle out. That's the law of reflection. Some of it will refract into the medium. And instead of going straight, it gets bent. Which way will it bend? Think of wave fronts, if you will. Say you got some wave fronts here coming in. And there's one here. All right, but some of these wave fronts are in the material. What happens to them?
They go faster than
Faster or slower? Well, let's decide that first. I think because of that, it's going to change speed. There's our answer. It's going to get bent and refract because it changes speed. Because the waves travel at a different speed in glass than they do in air. Hence the clicker question. But which way? Do you think they'll slow down or speed up? Who thinks slow? Who thinks fast? Okay, tell me why each of them. Tell me fast. It's more dense. It'll travel faster. Yes. And this is where I'm going to specify, and I just apologize. This confused me a lot, and I wish it was consistent. But it's not, and that's the point of chapter 26, properties of light. We now get to talk about light specifically, instead of just waves in general and sound. And there's a difference. With sound, the more interactions. If this was a sound wave, it does speed up in glass. Sound waves travel faster in glass than air because of those interactions. Think back to the dominoes. Those that were spread far apart didn't interact as often. So the wave transmitting through it was slower. Where the dominoes that were closer together had more interactions more often. And so the wave went faster. It won. That's the idea here with sound waves. Sound would go faster in glass. Light waves go slower. Just to throw you off and confuse you. But the key here is sound waves are mechanical waves, and they need the medium to vibrate. Light, electromagnetic radiation, does not need the medium to travel. It can travel on its own. So by going through a medium, it just kind of slows it down. It has to interact with it and slows down. So you can think of light comes in. To a molecule or an atom. And that atom absorbs it. And then there's an electron. It can cause to start vibrating. In the Bohr model, you got an electron, not drawn to scale, obviously. This a free electron can absorb it and gain energy. And so it starts vibrating. That makes sense. It can force vibrate it, or it can make it resonate. That'll depend on the frequency of light coming in. Well, it vibrates, and when it settles down, well, I should say first, by vibrating, energy is conserved. So the light comes in, that's energy. The electron's now vibrating and increases its energy. And one way to think of that is it goes up an energy level. Or it's got more energy in general. When it goes back down, or stops vibrating, it'll give up its own light in the form of energy. Its own energy in the form of light. So it gives off its own. And how do you think the frequency of that light compares to the frequency of this light? F in versus F out. What do you think? We got an equal and a higher. frequency, how fast it vibrates, kind of corresponds to how much energy it has. Higher frequencies have more energy and shorter wavelengths. So if magically the frequency could go up, energy came from somewhere. That doesn't happen. The energy of this light comes in with its frequency. It's transmitted to the electron, so it now has that energy. And when it gives up that same amount of energy. So it actually comes out with the same frequency light. You know this, you just didn't know you knew it. If you shine blue light into a piece of glass, what comes out the other side? Blue light. You didn't change it magically to red. Yes?
If we have an object that's transparent and another object that's from the same material that's opaque, but it's from the same material, the molecules are the same inside, why does the transparent one let the light out?
You're saying the same material, but one's transparent, one's opaque. If one's transparent and one's opaque, they're not exactly the same material, or they wouldn't be transparent and opaque. So there is something different.
What is it about the transparent material that lets light in?
There's a pigment there, and that adds material to the opaqueness or something.
But if there's like an obstruction, or there are molecules that absorb energy, why does it still let in the same amount of light?
Yes, and that's the whole point of this lecture is things that are transparent versus opaque. Why that difference? I think as we go along, it'll become a lot very clear. No pun intended. I'm just going to build on it so it makes more sense, because that is the whole point of this lecture. Get some foundational work here. But you got this, the frequency in's the frequency out. But what I like too is the light that comes in is not the same light that comes out. The same wave. It's different. This is absorbed by the electron. Then the electron emits its own wave. And then this can get absorbed by another electron. So it's kind of like the wave comes in, gets the electron vibrating, and it, as the author says, it burps, bloop, and emits its own wave. And it comes over to this electron, and it gets it vibrating, forced vibration, and then it bloop, bloop. Well, each of those interactions take time. And so when light travels through a medium, it slows down compared to in a vacuum or air, where it's going really fast. In air, it's slightly slower than a vacuum, but not much. But when you go through water or glass, it can slow down significantly because it has to interact with each of those. So back to don't be confused. Think about interactions with the speed of waves, but with sound, it's the medium that's vibrating. And so each of those interactions speed it up. Make it go through it more quickly, because it can be transmitted more quickly with each interaction. But with light, each interaction slows it down because it has to absorb the wave and then emit it back out. And that takes a bit of time. You with me? The intensity would be, for most things. Think of a piece of glass. You'll start with transparent. You have a flashlight behind you. Well, here's glasses. That light's so intense. I look through here, it looks just as intense. But yeah, the light that left the light bulb hits the glass is not the same light that enters my eye. What enters my eye is whatever left the last electrons. So that comes in, starts them vibrating, bloop, 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 and then it emits a last one that comes into my eyeball, and that's what you see. So light on its frequency can force electrons to vibrate.
So if we get a huge glass block, it wouldn't change the intensity of the light.
Okay, now you're thinking. If you get a really big block, say it's as long as this room, and you shine a flashlight on one side, do you think it'll be as bright over here on the other end? No, we know that. Common sense tells us, no, it's going to look dimmer. So all that light didn't make it through. Where'd it go? Where'd that energy go? Heat. It had to have. See, you guys are thinking. You got the thermodynamics. You got conservation of energy. This is ideal, and with one atom, it's pretty much perfectly ideal. But yeah, you get enough of those atoms, every time it makes vibrations, it's wiggling, right? That can create heat. So there you go. Things that are transparent, it makes it out. things that are opaque, it gets absorbed and doesn't re-emit. And so it goes to heat. So like this is opaque, the table. I'm opaque. This is opaque, this is opaque, this is... So light's coming into it, but it's getting absorbed or reflecting back off. It's not making it through. And we learned that dark things, like black objects, absorb better. And we're going to get the color, but white light comes in. It must be absorbed by this black pigment. And so it's not reflecting much light back out or letting it go through. That's why this warms up better than something that's white, because this is reflecting it back to our eyes. The electron can start wiggling and spit it back out. Mirrors are a good example. They're opaque because the light bounces right off of them. But they bounce it really well. And that's because metals, remember metals? They have a lot of free electrons that are not really attached to the atoms. They're free to move around, which is why they can conduct electricity really well and why they conduct heat really well. But it also means they reflect light really well, because the light comes in, makes the electron vibrate, it's attached to an atom normally. And so that vibration would cause its neighboring atom to vibrate and come through a normal piece of glass. But remember, in a metal, these are more free. In the valence band, if you remember that, they're free to move around. It's like they're not attached to any given atom. So they start vibrating, and when they give it up, it just bounces back out. It's a reflection. It's not really transmitted through the springiness of the atoms, if you will. So this is sort of reflective. This is really reflective. So those free electrons, there must be lots of free electrons absorbing the light, wiggling, forcing them to vibrate, but they're not really attached to atoms, so they don't really transmit it through. They bounce it back out. Whereas a piece of glass makes them vibrate, but they're attached to atoms, so it's emitted, makes the neighboring atoms vibrate, and neighboring electrons. They're all connected through molecular, Coulomb forces and quantum physics, and it'll come out the other side. That's transparency. And things that are just downright opaque, like this, they make the electrons vibrate, but it's all turned into heat. So there's some difference between reflecting, transmitting, and absorbing, opaque. Somebody had a question.
So this is kind of irrelevant, but in those in tinted glass windows or the one-sided mirrors, how does that work? Waves reflecting.
One-sided mirrors? Yeah, this is kind of like a one-sided mirror, but I have a black piece of metal on the other side. And so, yeah, if I lift up the black on the other side, I can see in. But it'll depend. If it's really bright in here, and I turn off the lights in there, this light will come to this, and it'll look like a mirror, and it'll reflect. So the electrons are forced to vibrate, but they're not attached to atoms, so it bounces back out. However, if we turn the lights out in here and I turn the lights on in there, it'd be the reverse. Then you could see through. The light would bounce off of the other side. So it's like a partially transmitted piece of glass. And they have those. Anytime they put coatings on there, you're somewhere in between a mirror and completely transparent. It's just changing that frequency that it wants to vibrate at. Exactly. Those, interrogation rooms and police shows, or in real life, yeah. If they turned the light on the other side, then the person being interrogated could see them. Yeah. It's just get rid of any light. Don't allow any light on that side to be emitted, so there's no light to transmit through, and you can't see them. Think of let's do this too. These are attuned to the same frequency. Here, let me convince you here. Don't really hear much of a beat pattern. But I can, like, light can come in, vibrate an electron. Do you know this vibrates the wood, forces it to vibrate, and waves come out, sound waves. Those sound waves can go in here and force that to start vibrating. And if it starts vibrating, we can get vibrations out on the other side. This frequency resonates with this frequency. Sometimes it kicks it more, sometimes it doesn't. Depends on its mood. So another way to think of absorbing, that's how I like to, is things that are opaque absorb the light. I think you got that. But why? It means that all this light energy, or more of it, is turning into thermal energy. That's why black heats up. It resonates. Things that are opaque resonate more at that light frequency. If this frequency is what this wants to vibrate at, then remember what happens to the amplitude? It's bigger and bigger and bigger. And that's going to get converted more to thermal energy. And so this energy will get converted to thermal energy instead of being re-emitted. So things that are transparent, that frequency light goes right through it. So that frequency does not resonate with the electrons in this, or the atoms and molecules for that matter. Ultraviolet light does resonate with glass. The electrons in glass want to naturally vibrate at the frequencies of ultraviolet light. And so does ultraviolet light get through? No. Glass is opaque to ultraviolet light. But it's transparent to visible light. And then we can get to infrared light. The electrons don't resonate at infrared light, but the atoms and molecules do. They absorb infrared, or heat waves. And so it makes them resonate so that infrared light is converted to thermal energy. And so infrared light doesn't make it through glass either. It's opaque. Most glass. There's different kinds of glass. So yeah, UV and IR don't make it through most glass. But visible does. Your remote control, it's fun for your TV. That's the very near infrared. It'll make it through a black trash bag. It might make it through your shirt. You ever try it? Change your channel? Because the black trash bag is opaque to visible light. It resonates with it and gets absorbed. But near infrared light, it's transparent. It passes right through. And it's because of the structure of the atoms and molecules of the material. And whether it resonates or not determines whether it's transparent or opaque. Do you remember doing our collisions way back when? I don't remember if I actually brought out Newton's cradle, but we had lots of collisions. And you take one, boink. But a lot of people are more familiar with these, so maybe it's a visual. You can have a light wave come in. It interacts with each of these. It makes each of them vibrate. And a different ball comes out the other end. But the same frequency. And if we had 1,000 of these spheres, it would take a lot longer for that to happen from this one. There's a time delay between going in and out. So light goes more slowly the more interactions there are. Something a lot of people don't realize too. It's not like light gets into water and just slows down. Only when it's getting absorbed. That just takes time. But when it's traveling here, it travels at the speed of light. When it travels here, in between electrons and atoms, it's traveling at the speed of light. But then it gets absorbed again. Speed of light, absorbed. Speed of light, absorbed. Speed of light, absorbed. But each of those absorptions and re-emitting delay it. So on average, the time through the glass would slow down. Now let's get back to your big piece of glass. Sure, glass is transparent. However, if you have a whole lot of those interactions, every time it slows down a little bit. I mean, it's dissipated a little bit. Some of this energy is converted to thermal energy. And so you don't have as much light eventually. It's like water. You go deep enough, you don't see the sun anymore. But we normally think of water as transparent. But you have enough interactions, you can create it opaque. All right, where are we at here? That was some good stuff. Did that. Oh, I haven't shown you what it looks like yet. Let's do that. So, I mentioned it before in this semester, but light is an electromagnetic wave. You can think of the red arrows as an electric field. The source of all waves is a vibration. And what's causing light? Your electromagnetic radiation. What's the source? Vibrating molecules? Yes, and mostly electrons. They're charges that are moving around. So they're vibrating. That's the source. They cause an electric field to vibrate, and it's changing. It goes up and down. We know about waves. There's an associated magnetic field, which we haven't discussed. Changes in electric fields create magnetic fields, and changes in magnetic fields create electric fields, hence electromagnetism. And a light wave is both of those, propagating through free space. But think of them as an electric and magnetic field always oscillating. And the reason they travel at the speed of light is it isn't some magic number. Maxwell actually figured out the speed of light. Here now we just, it's this, and we use it. The change in an electric field determines the strength of the magnetic field. If there's a greater change, you get a bigger result. Well, if the electric field were changing, let's say it was decreasing, not changing as quickly, then the magnetic field would be less. And it wouldn't be changing as much, which would make the electric field be less because they're driving each other, and eventually the wave would dissipate away. But it doesn't. And the reverse is true too. If they were getting increasingly bigger and bigger, the light wave would be going faster and faster and brighter and brighter and brighter, and we don't see that either. So the reason the speed of light is constant is really conservation of energy between these oscillating electric and magnetic fields. And that's why we say the speed of light is this. So remember, when I do say, the speed of light goes slower in water, it's really not changing how it's vibrating like that or propagating. It's just there's a time delay going through it because of all those interactions. And that time delay effectively slows it down throughout that material, by the time as if it wasn't there. And that can bend the waves also. So back to our piece of glass there. If it was sound, it would bend one way because it speeds up in the glass. But light would slow down and bend the opposite way. Both are refraction. The electromagnetic spectrum, we've discussed. It looks like this. We've labeled them before. So you can see at the top, increasing energy to the left, over on this end, where the wavelength's really short because it's vibrating really fast. Those are gamma rays and X-rays. You go a little slower, you got ultraviolet. Here's the visible. It's like 1/1,000,000th of 1% of the entire electromagnetic spectrum is all we can see. But technically, all of this is light. We can only see a very, very small portion. Our eyes are only receptive to visible light. You got your eyeball. There's your cornea. When the light waves come in from air into your cornea, 70% of the bending, the focusing power of your light is just because it changed mediums, went from air into your eyeball. Because we know it slows down in there. And so it bends, it refracts. 70% of that bending, that focusing, is just by entering. Then, we have lenses, and that will fine-tune the focusing and bend them even more. And if it doesn't land right on your retina, which is the back of your eyeball where your sensors are at, then you can't see clearly, like this. You guys are blurry. It just means it's not bending and coming to focus on my retina. So I need some help. It's either focusing too quickly, refracting too much, or not enough, farsighted or nearsighted. So you wear corrective lenses, help my eye out, and you're good to go. On the back of your eyeball, there's two types of sensors. They're called rods and cones. Cones are sensitive to dark and light, black and white. There's no color. But your cones are sensitive to low frequency light, medium frequency light, and high frequency light, which they peak in red, green, and blue. So we often call them red cones, blue cones, and green cones. So when I see your blue shirt cam, the frequency of that light enters my eye, hits my cones, and the only ones that react to it are the blue cones. They vibrate and they send a signal to my brain and it goes, you see blue. We're going to get into color more next lecture. But that's what's going on with the electromagnetic spectrum. Where are we at? Shadows. So, I'll save shadows for next time because I'm going to do these guys. This is all about resonance. So just remember, with light waves, if it doesn't resonate with the material, it'll make the things vibrate. It forces them to vibrate. If they're connected to the atoms, they'll re-emit to their neighbors and pass on through. It's transparent. If it resonates, though, a lot with it, it'll get absorbed and it's opaque. Like this. And the internal energy goes up. It gets warmer. If the electrons aren't attached to the atom, like in metals, they'll still be forced to vibrate and they'll re-emit the light wave but back at you. It'll reflect like a mirror. So it's all whether the incoming light resonates or not. So I was going to go back to some sound resonating demos to end with. These are boom whackers. Anybody seen these? They're just tubes that are flexible. And its length will determine the size of the wave. I need to force a vibration, so this is how they work. You whack them. But that one makes a different sound than this one. And that's because I make the air start moving inside, but it reflects at the ends. Remember, inside the air, it can be changing its pressure because it's a compression and refraction. But we have atmospheric pressure out here, right? So it's kind of like hitting a brick wall. And so some of it will reflect back, and there you go. You can create a standing wave. And the length determines the size of the wave, and thus how fast it vibrates and the note you hear. This one's half the length, so what do you expect? The wave will be, shorter, half the length, and the frequency will be how much higher? Twice the frequency. Yeah, so for you musicians, that's an octave higher. Let's do this. If I close this end off, what do you think will happen to the sound? Anything? The wave comes in and reflects and has to come back before you can hear it, make the air and hear it. So it's twice as long. So it's an octave lower than it was. So if we do that to this one, this is now effectively the same length as that. We call this an open tube and this one a closed tube. So the wave has to go down and back before it can make the air in the room vibrate. Twice as far. Same length as this. Same note. Now this is a tube with a wire mesh right here. I'm going to heat it up. I call it a hoot tube. Thank you. And you understand this. This makes the air hot, right? What does hot air do? It rises. And you know why now? Because it's less buoyant, less dense, so it goes up. So you get convection. That drives the air. Well, the length sets a standing wave up, that you hear. This one's a little longer, so what do you expect? It's made out of metal, so I can heat it up more. The wire mesh is here. Do you think it'll be higher or lower? It's longer, so it'll make a longer wavelength, which will vibrate more slowly. It's lower. If you're careful, you can pour the sound out. Even harder, back in. Now you know why that works, so think about that until next time. And I'll ask you, remind me, why does it not make sound when it's like this? It has nothing to do with the cup. That's your clue. See you later.